Something is happening with 3i Atlas that shouldn't be possible. Its tail moves like a swarm of fragments pointing toward the Sunday. Its brightness pulses every 16 hours with no known mechanism behind it, and its chemistry divides into two opposite hemispheres almost as if two objects were fused together. These aren't minor quirks. They break the models we use to understand interstellar visitors. If discoveries like this fascinate you, hit subscribe and drop a like, because what comes next is even stranger. We now have 3 important new updates about the interstellar object called 3i Atlas, and each one makes the situation a little harder to fit into normal comet physics. The first update comes from Harvard scientist Avi Loeb, who has released new calculations about the strange tail of 3i Atlas that seems to point toward the Sun instead of away from it. His work suggests that this feature might not be a single tail at all, but thousands of separate fragments moving together in a coordinated swarm. The second update is that new observations show the object is pulsing with a regular pattern roughly every 16 hours, and the source of that pulsing appears to be completely inconsistent with what we would expect from a natural comet. The third update is that fresh scientific data now indicates 3i Atlas is releasing different chemicals from opposite sides, almost as if it has two completely different surfaces exposed to space. To understand why these results are so unusual, it helps to slow down and look at each piece one by one. Before digging into the pulsing behavior and the chemical differences, we can start with Loeb's latest work, because it focuses on something we have been able to see for months: the shape and direction of the tail. Most people are familiar with the basic idea of a comet tail. When a comet approaches the Sun, ice and frozen gases near its surface begin to heat up and turn directly into gas. This gas carries dust particles away from the surface, and sunlight and the solar wind then push this material outward. As a result, comets usually grow tails that stretch away from the Sunday. 3i Atlas, however, has shown a structure that seems to do the opposite. Instead of a tail pointing straight away from the Sun, there is a narrow feature that appears to point back toward the Sunday. Astronomers call this kind of feature an anti-tail. It is not unique to 3i Atlas. Anti-tails have been seen before in a few other comets, including Comet Ehrend-Roland in the year 1957 and Comet Hale-Bopp in the late 1990s. So the basic idea of a tail that appears to point sunward is not new by itself. In those earlier cases, though, careful follow-up observations solved the mystery. When scientists watched those comets from different angles or at different points in their orbits, the anti-tails changed shape. With better data, it became clear that the anti-tails were not truly pointing toward the Sunday. Instead, they were normal dust structures that only looked strange because of the angle from which we were viewing them. In simple terms, it was a trick of geometry, like looking at a long, thin object from one angle and seeing it as a short dot, then from another angle and seeing its full length. As the comet moved and Earth moved, the geometry changed and the illusion went away. The tails could then be understood as standard structures pointing away from the Sun, as physics predicts. With 3i Atlas, that expected change has not happened. Astronomers have been watching this sunward structure for months. The viewing angle has shifted as both the object and Earth travel along their orbits. The phase of the orbit, the distance from the Sun, and the relative positions have all changed, yet the structure remains. It keeps its general orientation and appearance instead of fading or swinging into a more typical configuration. That persistent stability across many observations makes it much harder to explain as a simple viewing illusion. So the natural question becomes, what kind of real physical structure could produce a stable feature that seems to point toward the sun? Different teams of scientists have come up with different possible explanations, and these ideas are not small variations of the same model. They are very different pictures of what might be happening near this object. The first explanation stays as close as possible to standard comet behavior. It suggests that we might still be seeing a geometry effect, but one that depends on unusually large dust particles. In a typical comet, most of the dust grains lifted off the surface are tiny, smaller than common grains of sand. These tiny particles are very light, so sunlight and the solar wind can push them quickly and strongly away from the sun, helping to form a broad, sweeping tail. If the dust grains are much larger and heavier, however, they respond more slowly to the sun's forces. They do not accelerate as quickly and can follow more complex paths around the nucleus of the comet. When you have large, slow-moving dust particles, their distribution in space can create unusual tail shapes. Depending on exactly where Earth is relative to the comet and the sun, those shapes can line up in a way that makes part of the dust cloud appear to point back toward the sun, even though, in three-dimensional space, the particles are still being pushed outward. It is a question of angles, timing, and perspective. This kind of effect has been documented in a small number of comets. It is considered a known natural phenomenon. Because of that, many astronomers lean toward this explanation for 3I Atlas. They suggest that the antitail may be a dense sheet or stream of larger dust grains, shaped by the orbit and by the solar wind, and that our viewpoint happens to make this sheet line up in a way that mimics a sunward tail. Avi Loeb, however, has pointed out a serious problem with this picture when it is applied to 3I Atlas. For the large dust explanation to work for this specific object, his analysis suggests that the central body would have to be much bigger than what current observations indicate. From brightness measurements and other data, astronomers estimate that 3I Atlas is only about 3 miles in diameter. That is not small compared to many comets, but it is not especially large either. According to Loeb, if the tail we see were created by the kind of large dust distribution needed to produce such a stable anti-tail, the parent object would need to be significantly larger than 3 miles across to supply and maintain that structure in a natural way. Because of this mismatch, Loeb has proposed a very different mathematical explanation. Instead of relying on a single body shedding dust in a standard way, his model treats the structure near 3I Atlas as a swarm made up of many individual fragments. In his calculations, the sunward feature is not just dust sprayed out from one solid nucleus. It is a collection of many separate objects, possibly thousands of them, moving together along very similar orbits. These fragments would be grouped closely enough that, when seen from Earth, they blur into what looks like a continuous tail or spike. The strength of this approach is that it is based on precise orbital mechanics. The motion of each fragment follows the same basic laws of gravity that guide planets and comets. By adjusting the number of fragments, their spacing, and their individual paths, Loeb and others can test whether a swarm can reproduce the exact shape and stability of the observed feature. This is not a vague idea. It is something that can be checked against the recorded positions of the structure over time. In this picture, 3I Atlas might not be a single intact object with a simple tail. It could be the core piece of a much larger, broken system, surrounded by many fragments that share almost the same trajectory. The anti-tail would then be the visible trace of that swarm as sunlight reflects off each part. That would naturally explain why the structure remains stable across many different viewing angles and orbital phases, instead of being a thin sheet of dust that changes as the comet moves. It would be a coherent group of bodies moving together. This idea, if correct, would already make 3I Atlas very unusual among known interstellar visitors. Most comets and asteroids we have studied up close are either single bodies or clusters of a few large pieces. A stable swarm of many fragments traveling through the solar system would raise questions about how it formed, how long it can stay together, and what kind of event produced it in the first place. For now, though, the core point is simple. The tale of 3I Atlas is not easy to explain with our normal tools, and Loeb's calculations open the door to the possibility that we are not looking at a single natural nucleus with a standard tail, but at a more complex structure made of many parts moving in a coordinated way. So far, we have focused on the strange tale of 3I Atlas, and on Avi Loeb's suggestion that a different kind of mathematical model might explain what we see. His idea becomes clearer when we look at another property of this object that has worried astronomers for months, something called non-gravitational acceleration. Under normal conditions, if an object is moving through the solar system and nothing touches it, its motion should be controlled almost entirely by gravity. The sun pulls on it. The planets tug on it a little bit. If we know the mass of the sun and we know the path of the object, we can calculate where it should be in the future with high precision. This is what we call a pure gravitational path. 3I Atlas does not quite follow that kind of clean path. When astronomers track its position over time and compare it to the orbit that gravity alone would produce, they find a small but consistent mismatch. Something is giving the object a gentle extra push. That additional push is what scientists mean by non-gravitational acceleration. It is not mysterious by itself. In fact, this effect is very common for active comets. The usual cause is gas and dust escaping from the surface. When ice on or near the surface of a comet is heated by the sun, it can turn directly from solid into gas. This process is called sublimation. The gas flows outward into space, often in narrow jets. Every time gas shoots out from one part of the surface, it produces a small reaction force in the opposite direction, like a tiny rocket engine firing. Over weeks and months, these many tiny reactions add up and slowly change the comet's motion. The result is that the comet's orbit drifts a little compared to the path that gravity alone would give. We have measured this kind of behavior in many comets, so it is considered normal. Loeb's idea becomes interesting when we combine this known effect with the possibility that 3I Atlas is not alone. He asks what would happen if the main object were surrounded by a cloud of much smaller fragments or debris. In his picture, these fragments are not random pieces scattered all across the sky. They are traveling along with 3I Atlas, moving through space at roughly the same speed and in almost the same direction. The key detail is that these smaller fragments would not necessarily behave the same way as the main body. If they are small enough and inert, they might not be producing strong gas jets of their own. That means they would not experience much non-gravitational acceleration. Instead, they would feel almost pure gravity from the Sunday. In other words, the main nucleus of 3I Atlas would be getting nudged slightly by its jets, while the fragment cloud would be pulled along only by gravity. This sets up a slow separation between the two. At first, the difference would be extremely small and hard to notice. The main body and the fragments would all be moving together through space, and from a distance, they would look like a single system. But over time, the contrast between a path with a steady extra push and a path governed only by gravity would grow. The main object, with its jets, would drift slightly away from the Sun because the reaction forces from outgassing tend to push it outward. The fragments, feeling no such push, would continue to follow the orbit that gravity dictates, which leans a bit more sunward. Even though this difference is tiny at each moment, the distances in space are so large and the travel times so long that small effects have room to accumulate. This is where Loeb moves from a simple idea to a precise calculation. He asked a specific question. Given what we know about the non-gravitational acceleration of 3I Atlas, how far would a cloud of fragments lag behind or move ahead if they were not subject to that same acceleration? Using standard formulas from orbital mechanics, he calculated the separation that would build up over time. At the current distance of 3I Atlas from the Sun, which is about 160 million miles, he found that the offset between the main object and a cloud of non-accelerated fragments would be about 33,500 meters. That is a little more than 20 miles. From our point of view on Earth, this physical separation would not be seen as a line of individual points. It would blend together into a compact feature. The important quantity for observers is how large that separation looks in the sky, which is called the angular separation. Loeb's calculation shows that such an offset would appear as roughly 0.7 arc-minutes of angular separation. An arc-minute is a unit used in astronomy to measure small angles in the sky. There are 60 arc-minutes in 1 degree. For comparison, the full moon is about 30 arc-minutes across. So we are talking about a feature that spans a little more than 1/50th of the apparent diameter of the moon. That is small, but well within the reach of modern telescopes. What makes this more than a theoretical exercise is that the November images of 3I Atlas do in fact show a sunward glow with a size close to this value of 0.7 arc-minutes. The numbers from the sky match the numbers from the equations. For Loeb, this agreement between prediction and observation is an important point in favor of the fragment cloud idea. He also points out another reason the swarm scenario is attractive. If there really is a cloud of tiny fragments traveling with 3I Atlas, then the total surface area exposed to sunlight could be much larger than the surface area of the main nucleus alone. To get a sense of how dramatic this can be, imagine that there are 1 trillion separate fragments in the cloud. That is 1 followed by 12 zeros. Together, all of these pieces might weigh only 1,000th of the total mass of the entire 3I Atlas system. In other words, almost all of the mass would still sit in the main body, and only a tiny fraction would be spread out in the swarm. However, because each fragment has its own surface, the combined exposed area of the swarm could be enormous. Loeb estimates that the total surface area of such a fragment cloud could be about 100 times larger than the surface area of a single intact object with the same mass. This kind of increase matters a lot in comet physics, because surface area is directly connected to how much ice can sublimate at once. When sunlight falls on ice, it can turn into gas only from the surface that is directly exposed. More surface means more places where gas can escape at the same time. So if you take the same total mass and break a small part of it into many tiny pieces, you can dramatically boost the total area available for sublimation without changing the overall mass very much. More sublimation means more gas flowing out into space. More gas flow can make the object appear brighter and can feed longer, more noticeable tails and jets. This gives the fragment cloud model a natural way to explain several puzzles that astronomers have been dealing with. One puzzle is why 3I Atlas seems so bright for the size we think it has. Based on the estimated diameter of about 3 miles, Simple models predict a certain typical brightness. In reality, the object and its surroundings appear brighter than those models expect. A swarm with much more surface area would emit more reflected light and more glowing gas, lifting the brightness to the observed level without requiring the main nucleus to be larger than current measurements allow. Another puzzle concerns the rate at which 3I Atlas seems to be losing mass. When astronomers look at the amount of gas and dust it is releasing, the numbers suggest that it is shedding material faster than a simple solid object of that size should be able to sustain over long periods. If the nucleus were the only source, it might have to break apart or shrink quickly, with a cloud of fragments adding extra surface for sublimation. You can get higher mass loss rates while keeping the main body mostly intact. A third puzzle has to do with the shape of the jets themselves. Observations show jets that stay narrow and well collimated, instead of becoming widely spread out by rotation and other effects. A structured swarm could help maintain these narrow columns of material by providing many small, steady sources aligned along shared paths, rather than a single rotating source smearing everything out uniformly. For all of these reasons, the fragment swarm hypothesis is appealing. It ties the non-gravitational acceleration, the brightness, the mass loss, and the jet structure together into one picture. But it is important to remember that this is still only a hypothesis. It is a proposal that tries to connect several unusual observations with one underlying cause. It has not been confirmed by direct detection. Most scientists working on 3I Atlas still favor the more conservative explanation that relies on viewing geometry and large dust particles. That explanation is grounded in natural processes we have already seen in other comets. In addition, there is an important observational constraint. High-quality images taken on November 11th show that the nucleus of 3I Atlas still appears to be intact. Astronomers specifically looked for signs of obvious fragmentation by applying multiple image processing techniques to enhance any faint structures around the main body. They did not find clear evidence of large pieces breaking away. This does not entirely rule out the presence of a fragment cloud, but it does limit what kind of cloud could exist. Any fragments must be too small or too diffuse to show up as separate objects at the resolution of current observations. In other words, if a swarm of debris really is traveling with 3I Atlas, the pieces must be very small. They would be more like dust grains than miniature comets, subtle enough to hide within the glare of the main object, while still quietly shaping what we see. The observations so far have raised questions about fragments and non-gravitational motion, but another pattern is drawing just as much attention. Before getting into the unusual chemistry recorded around 3I Atlas, it helps to look carefully at the second strange behavior scientists are tracking. This one is not vague or hard to measure. It is one of the most precise repeating patterns ever recorded in the study of a comet. Astronomers have been watching how the brightness of 3I Atlas changes over time, and what they see is a steady cycle that repeats again and again. The object brightens in a clean, almost perfect rhythm about once every 16.16 hours. The timing does not drift. It behaves like a clock that does not lose or gain a beat. When this cycle was first noticed, the simplest explanation seemed reasonable. Many comets rotate, and rotation often causes the amount of reflected light to rise and fall as different parts of the surface come into view. If a nucleus has bright and dark patches or uneven terrain, its spin can produce a regular brightness curve. So early on, astronomers assumed 3I Atlas was simply rotating with a period of about 16 hours. That explanation held up only until researchers examined the data more closely. they found that the size of the brightness changes was far larger than what rotation alone could produce. To understand this, it helps to separate the two main components of a comet's visible structure. The solid nucleus is a compact central body made of rock, dust, and ice. The coma is the cloud of gas and dust that forms around the nucleus when sunlight heats the ice and turns it into vapor. For most comets, the solid nucleus contributes a noticeable portion of the total brightness. 3I Atlas does not behave that way. Less than 10% of the total light we see comes from the nucleus. More than 90% comes from the coma. This means almost all of the brightness variations arise not from the surface of the nucleus, but from the behavior of the gas and dust surrounding it. When astronomers tracked the speed of the gas flowing outward, they found values near 980 miles per hour. With that speed in mind, they calculated how far the gas travels during one full 16-hour cycle. The answer is about 15,900 meters. This distance happens to match the size of the region that brightens and fades in the images. The coma itself appears to swell with fresh gas and dust, then thin out, then swell again. It acts almost like a breathing cloud. Patterns like this are not unheard of. A periodic change in brightness, tied to rotation or to surface activity, has been recorded in several well-studied comets. Comet Halley showed a brightness cycle that repeated every 7 to 8 days. Comet C, 2013, a 1, sometimes called Siding Spring, showed a repeating cycle of about 8 hours. Comet 2P Encke displayed a pattern of about 11.5 hours. So the idea of a comet brightening and dimming in a repeating sequence is familiar. 3I Atlas differs from those examples in some important ways. In the other comets, the brightness changes were caused by the rotation of the nucleus. As the surface turned, areas with different brightness came into and out of view. But in 3I Atlas, the nucleus does not drive the pattern. Almost all of the brightness changes come from the coma itself. Instead of simply presenting different surfaces to us, the object appears to release bursts of gas in a repeated rhythm. With each cycle, the coma grows and brightens as fresh material streams out, then slowly fades as the material disperses. The size of these swings is also notable. The amplitude of the changes reaches tens of %, which is unusually high. This suggests strong periodic outgassing, meaning that gas does not escape at a steady rate, but in pulses. What could drive such behavior? The simplest natural explanation is thermal cycling from one or more active ice regions on the nucleus. Ice on the surface of a comet reacts strongly to changes in sunlight. If a portion of the nucleus contains a large deposit of ice, and if this region faces the sun only once each rotation, then that region would heat up and release gas quickly when illuminated. As the nucleus continues to rotate, the active region would turn away from the sun, cool down, and release gas more slowly. 16 hours later, it would face the sun again and produce another strong burst. Over time, this combination of heating and cooling would create a repeating pattern in which the coma fills with new material, then thins out, matching what observers are seeing. In this picture, the nucleus does not need dramatic changes in shape or unusual rotation patterns. It only needs an ice deposit that heats rapidly when exposed to sunlight. Even a slight difference in temperature can cause ice to sublimate much faster. As gas escapes, it carries dust with it, and both gas and dust increase the brightness of the coma. When the active region rotates away from the sun, sublimation slows down and the coma dims. This cycle repeats every time the nucleus completes another rotation. Avi Loeb has suggested a way to test whether this natural explanation is correct. The The test relies on the direction of the jets that drive the pulses. If solar heating is the cause, then the jet responsible for each brightening event must point toward the sun at the moment the pulse occurs. That is the only direction from which enough solar energy could reach the ice and trigger the burst. So, if the pulses are caused by sunlight striking an ice pocket, the orientation of the jet should always be aligned with the sun during the bright phase of each cycle. This idea is testable with repeated imaging and careful tracking of the jet's direction. Loeb also notes the alternative. If the jets appear to pulse in directions that do not match the sun's position, then the natural thermal cycling explanation becomes harder to support. Solar heating cannot produce strong gas release from a surface facing away from the sunday. If future observations show the pulses happening in angles that have nothing to do with solar illumination, then another mechanism would need to be considered. That does not imply anything unusual by itself, but it would mean the standard picture does not account for all the data. At the moment, the thermal cycling model still fits the observations well. Scientists continue to study the brightness curve, the coma structure, and the direction of the jets to confirm whether the 16-hour pattern behaves exactly as a solar-driven cycle should. The more complete the data becomes, the clearer it will be whether this repeating pulse is simply the result of regular heating and cooling of an exposed ice region, or whether another process is shaping the behavior of 3I Atlas. Astronomers have been working for months to understand what 3I Atlas is made of, and what kinds of chemicals are escaping from its surface. Many telescopes have observed it, but the most decisive information has now come from a system that can identify molecules directly, the ALMA radio telescope. ALMA, which stands for the Atacama Large Millimeter Array, does not take pictures the way optical telescopes do. Instead, it detects the faint radio signals that different molecules give off as they float in space. Each molecule produces a specific pattern, almost like a fingerprint, and that pattern allows scientists to know exactly which substances are present around an object. When ALMA observed 3I Atlas, it detected two molecules that are extremely common in comet studies: methanol and hydrogen cyanide. Both appear regularly in comets from our own solar system, and both have been measured countless times. Just finding these two did not surprise anyone. What caught scientists' attention was not the chemicals themselves, but the ratio between them. According to the first set of ALMA data, the methanol to hydrogen cyanide ratio in 3I Atlas was about 124 to 1. 3 days later, when the object was observed again, that ratio had changed to about 79 to 1. Even though both values are very high, the ratio itself is not stable, which adds another layer of complexity to the picture. To understand why these numbers shocked scientists, it helps to know what is typical. In ordinary comets, the methanol to hydrogen cyanide ratio usually falls near 10 to 1. Sometimes it goes as high as 20 to 1, but not often. Out of the thousands of comets that scientists have measured, only one known object has ever shown a ratio as extreme as the numbers coming from 3I Atlas. That comet is C2016 R2 Pan-STARRS. It had a methanol to hydrogen cyanide ratio of about 100 to 1, a value so unusual that researchers consider it a rare outlier. What makes that older object even more unusual is that we still do not have a clear explanation for its chemistry. Scientists have modeled many possible formation paths, but none of them solve the puzzle in a satisfying way. C2016 R2 is simply viewed as a chemical exception, something that formed under conditions we do not yet understand. Until now, it stood alone. The discovery that 3I Atlas shows nearly the same extreme ratio is striking, but the story becomes even more puzzling when you consider where each object came from. C 2016 R2 formed inside our own solar system. It was shaped by the history of the disk of gas and dust that surrounded the early Sunday. 3I Atlas, however, formed in a completely different star system, many light years away. There is no direct connection between the two birthplaces. The stars were not related. The clouds of gas and dust that built each object were not shared. They came from entirely different environments in the galaxy. Despite that, both objects show nearly the same kind of chemical imbalance. Two bodies formed under unrelated conditions, separated by enormous distances, ending up with nearly identical extreme ratios, is the kind of coincidence that stands out in comet science. It suggests that either the process that created C 2016 R2 is more common outside our own system than we thought, or that there are still basic aspects of comet chemistry that we do not fully understand. For now, it simply means that 3I Atlas has joined an extremely small category. But ALMA did more than measure how much of each molecule was present. It also mapped where each molecule was coming from across the surface of the object. This level of detail is rare in comet observations. Many telescopes can tell us which molecules are present, but not where they originate. ALMA's spatial resolution makes it possible to separate the emissions coming from one side of the comet from those coming from the other. When scientists analyzed the distribution of methanol and hydrogen cyanide around 3I Atlas, what they found deepened the mystery even further. Methanol was concentrated on the hemisphere facing the Sunday ass. 3I Atlas travels along its orbit. One side of its surface receives direct solar radiation. That sunlit side is actively releasing methanol at much higher rates than the hemisphere facing away from the Sunday. This is not entirely surprising by itself. Many molecules become more active when warmed by sunlight. Methanol, like many ices, sublimates faster when heated. So a sunward concentration of methanol makes physical sense. The unusual part is not that methanol responds to sunlight, but how strongly and how unevenly the response appears. Hydrogen cyanide, however, shows the opposite pattern. Instead of being concentrated on the sunward side, it is strongest on the hemisphere, pointing away from the Sunday. That means one molecule is most abundant where sunlight is strongest, while another molecule is most abundant where sunlight is weakest. The result is a comet-like object with two chemical faces, each dominated by a different molecule. The side heated most directly by the sun is bright in methanol. The shaded side, far cooler, is dominated by hydrogen cyanide. That spatial separation is extremely unusual. In a typical comet, we expect the distribution of different molecules to follow the same general pattern, because solar heating controls much of the activity. Molecules with similar sublimation temperatures usually behave in related ways, especially at the distance where 3I Atlas is currently located. When sunlight warms the nucleus, the heat penetrates a short distance beneath the surface, and many different ices begin to sublimate at similar times. That process tends to blend their emissions, creating a coma where the molecules are mixed together rather than completely separated into hemispheres. Seeing methanol and hydrogen cyanide coming from opposite sides is therefore inconsistent with the simple picture of a comet warmed by the Sunday. It requires something more complex happening inside 3I Atlas, some combination of internal structure, composition, or thermal properties that produces sharply divided hemispheres. One possibility is that the nucleus contains different kinds of ices in different regions. Another possibility is that the surface has been processed in a way that exposed different layers on different sides. In comets that formed in our own solar system, such asymmetry is rare because the object is expected to be mixed well enough that no single region dominates one type of molecule by such a wide margin. With 3I Atlas, the separation is not small. It is not a slight increase from one side to the other. It is a strong and clear difference, large enough that ALMA detected it easily. This raises questions about the internal structure of the object. If it formed in another star system, its early environment might have been much more varied than the disk of gas and dust that formed the planets and comets around the Sunday. The distribution of materials in its birthplace could have been uneven, leading to a nucleus with strongly layered chemistry. But even if that is true, the fact that the hemispheres appear so cleanly divided still stands out. Another point that makes the situation more complex is the rapid shift in the methanol to hydrogen cyanide ratio over just a few days. The ratio did not remain at 124:1. It dropped to 79:1 in a short period. That kind of change suggests that different parts of the nucleus may be exposed at different times, or that solar heating alters the release of materials in a non-linear way. If one hemisphere contains most of the methanol and the other contains most of the hydrogen cyanide, even small changes in the orientation of the object relative to the Sun might shift the ratio noticeably. The drop in the ratio also shows that the chemistry of 3I Atlas is not static. It is evolving as the object travels along its orbit and as different areas heat and cool. This kind of rapid evolution is not unheard of in comet science, but combined with the extreme values involved, it points to an object that is behaving outside the usual categories. Because the methanol is concentrated on the sunlit side, we can infer that this hemisphere responds strongly to heating. A slight increase in solar energy may cause a sharp increase in the release of methanol. Meanwhile, the hemisphere away from the Sun does not behave like a simple, cooler version of the same surface. Instead, it responds differently, releasing hydrogen cyanide in larger amounts even though it receives far less heat. The reasons for this are still unknown. Scientists do not yet have a clear explanation for how one half of a nucleus becomes dominated by one molecule, while the other half becomes dominated by another. The only thing we can say with confidence is that 3I Atlas has a divided chemical structure. One hemisphere is a strong source of methanol. The other hemisphere is a strong source of hydrogen cyanide. It is a pattern that does not match what we expect from a typical comet, and it adds to the growing list of properties that make this object difficult to categorize. How these hemispheres formed, why they became so different, and what they reveal about the birthplace of 3I Atlas are questions that researchers are still trying to answer. For now, all we can do is study the emissions, compare them to what we know from other comets, and acknowledge that the behavior we are seeing methanol from the sunward side and hydrogen cyanide from the shaded side is unlike anything routinely found in the comets that formed around our own star. And with that, we reach the final point of the new ALMA findings. The hydrogen cyanide is not simply mixed in with the methanol or emerging from a broad blended area. It is concentrated on the side, pointing away from the Sunday. The chemical data reveal that 3I Atlas is far more complex than a simple uniform block of ice and dust. Its two hemispheres appear to have different dominant materials, each releasing a different molecule into space. This means we are not looking at a nucleus with small patches of variation scattered across the surface, which is something seen in many comets from our own solar system. Instead, we are observing a large-scale split that runs across half of the object. One hemisphere favors methanol, the other favors hydrogen cyanide. In practical terms, it behaves as if two distinct sources of material were pressed together into a single body. This kind of global chemical division has never been documented in an interstellar object before. Earlier visitors from other star systems passed too quickly or were too small for us to observe their chemistry in detail. Oumuamua was close but faint, allowing only limited study. Comet 2I Borisov gave us more information, but still not enough to map chemical differences across its surface. 3I Atlas is the first case in which we can examine an interstellar body with enough clarity to see how its composition changes from one side to the other. That makes this object an important piece of evidence about how small bodies form around other stars. To appreciate why the chemical split is so unusual, it helps to consider what scientists normally expect from a comet's interior. In most cases, comets are mixtures of dust and ices formed in cold regions far from their home star. Their building blocks come from the same surrounding cloud of gas and particles. As these clumps grow, the materials inside tend to mix through repeated collisions, rotation, heating, and cooling. Over time, this leads to a fairly even distribution of ices such as water, carbon monoxide, methane, carbon dioxide, and methanol. Local variations do exist, but these usually form small regions rather than entire hemispheres. Pockets of ice or sealed fractures can release more gas in some places than others, but the bulk composition is still relatively balanced. By contrast, the chemical pattern seen in 3I Atlas is not subtle. Instead of scattered variation, it shows a strong separation where the molecules prefer one hemisphere or the other. In our solar system, the closest parallel might be comets that have active jets emerging from limited areas. These jets indicate that certain regions heat up more quickly or have easier access to sunlight. But those cases involve differences in activity, not differences in underlying chemistry on a global scale. Nothing in our catalog of comets looks like an entire hemisphere devoted mainly to methanol and another hemisphere devoted mainly to hydrogen cyanide. If we try to explain this pattern by using the simplest possible idea, layered ices from the time of formation, several problems appear right away. In theory, it is possible for a comet to grow in stages. If the environment around the forming object changes over time, different layers may trap different molecules. One era might supply material rich in methanol. A later era might supply material rich in hydrogen cyanide. If these layers built up unevenly, they might create a nucleus with sections that differ. But a layered history alone cannot explain the specific pattern we see now. A major obstacle is the steady rotation of 3I Atlas. It spins once every 16 hours, meaning that every part of the surface experiences sunlight and darkness repeatedly. When sunlight hits a surface, even briefly, it can heat the material, release gas, and open fractures. These processes mix the upper layers and expose new material. Over very long periods of time, such rotation tends to smooth out the differences. Any strong layering at the surface would likely wear down, crumble, or release gas from both types of molecules in a more blended way. For 3I Atlas to maintain two hemispheres with opposite chemical behavior for billions of years, all while rotating thousands of times, is hard to reconcile with this formation scenario. The second idea involves cosmic rays. These high-energy particles travel across interstellar space and strike objects at random. When cosmic rays hit surface material, they can break chemical bonds, create new molecules, or alter the composition of ice over time. If one hemisphere of 3I Atlas somehow received more exposure to cosmic rays than the other, its chemistry could shift in a distinct way. But this scenario also requires a stable orientation that never changes. The object would need to present the same side to the cosmic ray source for extraordinarily long periods. With a rotation of 16 hours, no part of the surface stays pointed in any one direction for more than a short interval. That repeated cycling through all angles makes it nearly impossible for one hemisphere to receive significantly more cosmic ray exposure than another, even if some small difference accumulated early in the object's history. Billions of years of rotation and heating would gradually erase it. The idea of cosmic rays creating a long-lasting hemisphere-scale difference is therefore inconsistent with the physical behavior of a rotating body. For this reason, most scientists consider the cosmic ray explanation to be implausible. It does not match what we know about how materials respond to billions of years of exposure. Because both explanations fall short, researchers have so far avoided offering a definitive interpretation. Instead, they are treating the chemical division as an open question. This is a careful, scientific approach. When an observation does not fit existing models, and when no proposed mechanism aligns with known physics, the correct response is to gather more data and consider that the current understanding may be incomplete. 3I Atlas now sits in exactly that position. Its chemical behavior challenges the assumptions scientists usually apply to comet-like objects. At the same time, the chemical anomaly is only one piece of the broader picture. 3I Atlas has already displayed unusual patterns in its tail, its brightness cycle, and its non-gravitational acceleration. Each of these features has prompted additional study. For example, the stability of the sunward structure raises questions about whether we are seeing a geometric effect or a coordinated group of fragments. The periodic brightening that repeats every 16 hours appears to come from gas in the coma, not from variations in the nucleus. And the slight but measurable departure from the gravitational path suggests strong activity that is difficult to model with standard assumptions. In many comets from our own solar system, one or two of these oddities might appear. A comet might show unusual jets or unexpected rotation, or its chemical ratios might deviate from the usual range. But 3I Atlas does not present a single anomaly. It presents several, all at once, and each one raises its own questions. The challenge is that none of the standard explanations easily account for the full set of observations. A model that explains the periodic pulsing does not explain the chemical split. A model that explains the chemical split does not explain the tail geometry. A model that explains the tail geometry does not account for the non-gravitational acceleration. The pieces do not yet fit together. This is not unusual in science. When researchers encounter data that do not match current expectations, they test the data, challenge their assumptions, and look for patterns that might point toward a deeper explanation. Sometimes small anomalies disappear after more precise measurements. Other times, anomalies remain and eventually reshape our understanding of a subject. But the first step is always the same. Identify the parts that do not fit, evaluate the reliability of the measurements, and consider whether a more complete model might be needed. In this case, the chemical mapping provided by ALMA is strong evidence. The instrument has very high precision and specializes in identifying molecules. Its detection of methanol and hydrogen cyanide on opposite sides of the nucleus is not a weak or marginal signal. It is clear, repeatable, and consistent across multiple observations. For that reason, the chemical division must be taken seriously. It is not an artifact of noise or a misinterpretation of low-resolution data. It is a property of the object itself. When combined with the other unusual features of 3I Atlas, This finding suggests that the object may have a history or internal structure not yet represented in our catalogue of comets. We do not know whether it formed from the collision of two separate bodies, whether it collected materials from different regions of its home star system, or whether some process unknown to us shaped its composition. Each of those possibilities would require additional assumptions, and none currently align with all of the existing evidence. Because the cause is not yet understood, the discovery has encouraged researchers to revisit earlier ideas and look more closely at small bodies beyond our solar system. Interstellar objects offer rare opportunities to study environments we cannot directly observe. They may contain clues about the chemistry and physical conditions around other stars. The chemical split in 3I Atlas is a reminder that the diversity of small bodies in the galaxy may be wider than previously thought. It may also indicate that some formation environments produce structures and compositions that we have not encountered before. Within the scientific community, some researchers focus narrowly on the models they believe can explain the observations. Others examine broader possibilities. Avi Loeb is one of the latter. Although his ideas about potential technology are not widely accepted, he continues to focus on each anomaly with close attention. He looks at the unusual tail structure, the non-gravitational acceleration, the repeated brightness cycle, and now the sharp division in chemical composition. His approach is to examine the inconsistencies and test them against known physics. Even when most researchers disagree with his conclusions, they recognize that he is one of the few who is working to address all aspects of the data at once. That willingness to examine the anomalies directly is part of how science advances. Unusual data invite questions, and questions lead to new experiments, new observations, and eventually new models. For now, 3I Atlas remains a collection of unusual behaviors without a single unifying explanation. Its surface chemistry does not match typical cometary structures. Its rotation does not smooth out differences the way we expect. Its interior composition remains uncertain, and its large-scale chemical split challenges the standard frameworks used to describe small icy bodies. Despite the disagreements around specific interpretations, the scientific value of studying these anomalies is clear. Each unexplained feature pushes researchers to refine their models and test whether the tools used to describe comets in our solar system can apply to bodies formed around distant stars. Even without adopting any of Loeb's more speculative ideas, it is important to recognize that he is one of the only researchers actively trying to explore the anomalies of 3 Atlas.